study of space-time algebra and geometric algebra in general. And we stopped last lesson at, where were we? We had done bivectors, we'd done reversion and inversion, we'd done reciprocal bases and tensors. We were working on the canonical form of bivectors, canonical form. And for this one section, I plan to diverge from the text of this paper and go to another paper where I was a little bit more comfortable with the explanation. This is the section of the paper that we're reading that talks about the canonical form of a bivector. And basically what they're after is, if you have a bivector f, you want to write it as a canonical bivector and a phase factor. And we understand this phase factor to be exactly the same as you would for a complex number. For example, they show it right here. The exponential of 2 phi I is cosine 2 phi plus I sine 2 phi, where I now is our pseudo-scalar basis vector. So this is grade 0 and this is grade 1. So when you look at EF, you're actually looking at a multivector. It's not written in our standard multivector form, but that's what this is. This is a grade 0 plus grade 4 multivector. And what they're trying to say is that if you have a bivector f, any bivector f, you always can have this grade 0 plus grade 4 multivector multiplying a canonical f. And that canonical f will always have a negative signature in this convention. And then they show you how to calculate phi in terms of the grade 0 part of the magnitude of f squared and the grade 4 part of the magnitude of f squared. The grade 0 part of the space-time square of f and the grade 4 part of the space-time square of f. Now the grade 4 part, of course, is a real number times I, so you have to multiply by this I inverse to clear it, to get it to be a real number. So you can take this ratio, calculate the inverse tangent, divide that by 2, get phi, and that phi will become part of this unit multivector, grade 0, grade 4 multivector, that has unit magnitude. Then you can calculate f through, you can calculate the canonical form by just running this equation in reverse, inverting this equation. Unfortunately, I had a little trouble getting through this. I thought it was a little terse, and also there's some real confusion for me regarding what they mean by magnitude of f squared, right? The magnitude of f squared, this I understand, right? I understand the 0th order of the space-time square of x, the 0th grade of the space-time square of x. But here you see the magnitude of f squared, and in the paper they define the magnitude of a multivector is its reversion, the 0th grade 0 part of the reversion, its magnitude squared, plus the grade 4 part of the reversion of the reverse square. I guess you would call this not the reversion, but the reverse square, grade 0 part. The grade 4 part of the reverse square, which is going to be a grade 4 object, but you clear the quad vector, basis vector out. This ends up being a real number. You square it, you add these two things together. So I couldn't quite reconcile this with the work in the paragraph that describes all of this. So what I did is I went to a different paper, a paper by Hestenes himself. Let's actually begin with a little bit of errata. Some viewers have pointed out some errors. And in particular, in lesson 13, I miswrote the contravariant form of, I miswrote the 2 form. And I had, this isn't a form. I miswrote the 2 tensor, or the 0,2 tensor f. And I had 2 superscript mu's on the 2 different 1 forms. And in other words, I had this nu was written as a mu, so there would be two mu's, and those two mu's would not marry up with the mu and the nu in the Einstein sum that's required. So that's an easy one. That's an easy error, and the way I've written it here is correct. All right, so that's lesson 13. In lesson 12, I went over to a chart in the paper, and I was fumbling around trying to find the grade 4 part. So let me go back to that. You may remember I was sort of looking at this, and I was saying, okay, this is the symmetric part here, right? This is the symmetric part, and this is the antisymmetric part. And I said, well, okay, this is the grade 0, and this is the grade 2. Well, what's important is that this dot product part, this symmetric part, is actually the grade 0 and the grade 4 part. Because I actually was trying to think that this bivector cross product thing, which we'll talk about later, I was thinking, was that the vector 4 part? Where's the vector 4 part? But of course, the answer is astonishingly obvious. But whenever you take the multi-vector product, well, you have a multi-vector M and a multi-vector P, and you take the space-time product of that, you can always write this as MP plus PM minus plus MP minus PM, all over 2, right? You can always break a space-time product between any two multivectors into a symmetric part and an antisymmetric part. And what's going on is when you do that, the symmetric part will take up a certain number of the relevant blades, right? So if M was, let's do something crazy, right? Say P was, let's just say they were K blades, and P was a 7 blade, and M was a 3 blade, right? So you would expect the space-time product to contain, in generality, a 7 minus 3 all the way up to 7 plus 3 blades, right? And those will be in steps of 2, right? They'll each be in steps of 2. So you would expect a 4 blade, a 6 blade, an 8 blade, and a 10 blade, right? In this product, right? So the question is where do these blades live inside the symmetric and antisymmetric piece? The symmetric piece will absorb some of these blades, and the antisymmetric piece will absorb the others. And which ones go where kind of depend on the degree or the grade of M and the grade of P, assuming it's a pure grade. I'm calling a pure grade thing a blade, right? Which doesn't necessarily have to be there's that whole issue of the definition of a blade, but a grade 3 multivector M and a grade 7 multivector P, right, would end up with a grade 4 part, a grade 6 part, a grade 8 part, and a grade 10 part. And those parts will be distributed in these two, right, in the symmetric piece and the antisymmetric piece of this space-time product. Well, if M and P are 2 blades, it turns out, and I've worked it out here, I have, if A and B are two grade 2 bivectors, well, A and B are bivectors, and I blow them up in components, you'll see that there's a grade 4 part, a grade 2 part, right? This is a grade 2 part because these guys right here are all bivector unit vectors. And then there's a grade 0 part, right? A grade 0 part. Everything here is a real number. And that is, of course, a quad vector. And if I reverse the order of those two, if I take the product of A and B in the reverse order, right, the grade 4 part is actually the same as the grade 4 part doesn't change. The grade 2 part actually changes into its negative, and the way you can see that is the bivector gamma mu beta ends up down here as gamma beta mu. So you're going to get a sign change, and so the grade 2 part in the commuted spacetime product is going to have a different sign. But the grade 0 part is not going to have a different sign. And as a consequence of this, if I take the symmetric sum, I get twice the grade 4 part plus twice the grade 0 part. And if I take the antisymmetric sum, I get twice the grade 2 part. So the antisymmetric sum is the grade 2 part all by itself. But the symmetric sum is the grade 4 part and the grade 0 part together. So that's where the missing grade 4 part went when I was fumbling around in that lesson. Okay, so that answers that question. And then this other errata really annoys me because I should have caught it. But I was really struggling with how to describe the inverse of a bivector, a basis bivector, right? So if we have gamma mu nu, which is defined as the space-time product of gamma mu and gamma nu, which because of orthogonality is equal to gamma mu wedge gamma nu, right? We all know that. But I want to talk about the inverse. And what I said in the lesson is that, the inverse of that is just going to be gamma mu nu. You just raise the two indices and you should get by definition the inverse. And that's only true for the basis vectors themselves, right? The basis vectors themselves, it is definitely true that gamma mu in the reciprocal basis is by its definition the inverse of gamma of the reference basis. But for bivectors, we really should use this definition of the inversion. And that is the reversion of the bivector divided by the reversion square. And the reversion of the bivector is, of the bivector gamma mu nu, is gamma nu mu. So to get this inversion, we have to write, we literally write this down. And when we do this calculation, this becomes a real number down below. Note there's no absolute values here. And you get gamma nu squared, gamma mu squared. This will often be 1, but it could be -1 if mu or nu are 0. Well, they can't both be 0 because then the numerator would be 0. But this will either be 1 or -1. But notice the top is the reverse. It's now gamma nu mu, right? You flip the indices around to get that inversion. So the inverse of gamma nu mu is gamma mu nu is gamma nu mu divided by this factor, which may be -1. Now we just look at the same definition for the inverse of an arbitrary reference vector, right? It's the reversion of that reference vector divided by the reversion squared, right? The reversions, or the square reversion. But of course the reversion is equal to itself, so you just get gamma mu over gamma mu squared. And the point is this is what this term here is actually, this is exactly this pattern here and this pattern here. And we are defining this, right, by definition is gamma superscript mu. So what this means is that the final equal sign here is in fact gamma superscript nu wedge gamma superscript mu, which is gamma nu mu. So the correct way to write this inverse is gamma nu mu, right? With these indices flipped from those indices. So that's an error, and it's the second time I've been caught by that flipping of the indices with the bivectors. You may remember I was caught by that when we did the demonstration of taking components. Okay, so that's enough for errata. So let's now move on. And when I say Hestenes himself, as though he's the, I guess we're treating this man as the spokesperson of this whole geometric algebra way of looking at space-time physics. And he wrote this paper called Space-Time Physics with Geometric Algebra. We're certainly not going to go through this whole paper. I'm just going to go through this one section to get us through. That's the equivalent section in the paper we're reading. You can find this paper at Dr. Hestenes' website, which is given right here, geocalc.class.asu.edu. And it links from here somewhere. But ultimately, this, or you can just look up this paper and find the link directly. And the part of the paper that we're going to study begins here on, I'm not sure what page it is, but it begins in this section right here. So let's begin, read this, and see if we can make contact with the material in our paper. So it starts with a very simple definition. The magnitude square of a multivector is the grade zero part of the reversion square. This definition, that I understand. That's really clear to me. Because this object is sort of a square, right? And so you wouldn't expect to see a square here because you're kind of dealing with something squared. You're dealing with a second order expression in a space-time product. And so this I understand. And because it's got no index here, right? When there's no index, you assume it's the grade zero part. Right? So it's the grade zero part of the reversion squared is what they're calling the magnitude squared for any multivector. Any multivector. So imagine, you can have a multivector with all of these parts in it, right? Now this is the reversion of M, but M itself would be, we would just write M itself with all these plus signs, right? So you can have any multivector, you multiply it together, you get all these different parts back, but the magnitude is all focused on alpha, according to this definition, right? Well, it'll be focused on after you do the reversion, after you do the reverse square, you're going to end up with some multivector because M times its reversion is a multivector. And whatever the zero order term of that multivector is, that's the magnitude. So then he says any multivector can be decomposed into the sum of its even parts and odd parts. And that's pretty straightforward. We know that the even parts of any multivector is the grade zero part, the bivector part, and the quad vector part, or the grade 4 part. Now notice in this paper, they don't use a capital I, they use a little I. And I much prefer the capital I because the little I just literally looks like a complex number. But that does go to show you how literal they want you to take our ability to treat I as though it's a complex number. Here they don't even hide behind some kind of special symbol, capital I. They're just all in with complex numbers on this. But despite that fact, when you see that complex number there, it is to be understood exactly like in our paper as capital I, and it's definitely to be understood. So this I is defined by that capital I, which is literally defined as gamma 0, 1, 2, 3. All right? So make no mistake about it. We're switching papers. The notation moves over a little bit, but it's still the same thing. Now, the odd part of this algebra is given by the vectors and by the pseudovectors, right? So if you add the vectors to the pseudovectors, that's a grade 1 part. That is a grade 3 part. Now notice, the grade, this A does not change under reversion, but beta I does change under beta I doesn't change under reversion, nor does A change under reversion, right? Beta I and F change under reversion, but alpha does not. So just because you're in the even part doesn't mean everything in here changes sign under reversion. In fact, for a general multivector M, the only things that change under reversion is the sign of the bivector part and the sign of the trivector part. All these other three parts stay the same, right? And here's a little happy equation you can use to figure out given the multivector itself, you can use this to separate out the the even part and the odd part if you ever needed to. Okay, so let's move on. The set of all multivectors that are only of this form, right? All even multivectors. The set of all even multivectors forms an important subalgebra of the space-time algebra called the even subalgebra. So now the reason it's a subalgebra, of course, is because any element of this set with the space-time product with another element of this set will produce another element of this set. So even times even multivectors, space-time product, another even multivector will give you an even multivector. So, so that's called the even subalgebra of our space-time algebra. The elements of the even subalgebra only have scalars, bivectors, and pseudoscalars, right? They have no vectors and no trivectors. And when I say trivectors, I really should start using the word pseudovector. If I'm going to call this a pseudoscalar all the time, I should call this a pseudovector. But notice that the way they write it, you always see it as the dual of a vector. But when you see the dual of a vector, you now need to be thinking pseudovector. And when you hear pseudovector, you think trivector. And so that's part of the conventions that you have to sort of work through in order to understand all this. So then they go on in this paper. If psi is an even multivector, meaning a member of M plus, then psi reversion is also even, but its bivector part must vanish according to equation 20. Well, this is equation 20, right? Equation 20 shows that the reversion of any multivector is the same multivector with the sign changed for the bivector and the sign changed for the trivector part. But since the reversion of a reversion square is equal to the reversion times the reversion, if the reversion of a reversion squared is equal to the reversion square, right? The only way that can be is if the reversion square does not have anything that changes sign, right? And if you're in the even subalgebra, this isn't even there. You don't even have the pseudovector part. You would only have a bivector part. But in the reversion square, that bivector part must go away, or else this expression wouldn't be true. So we can actually check this. Let's take an even member of an even multivector, right? Just scalar, pseudoscalar, and bivector. And let's just go ahead and multiply it by its reversion and see what we get. And, well, find the reversion square of an arbitrary even multivector. And I came out with this collection of things. It has this scalar part here, and it has a bivector part here, which has to go away, so it's canceled with this bivector part there. So that cancellation eliminates the bivector part. That's a pseudoscalar part, which is fine. And this is a bivector product that we're going to have to look at. But here is another, this is another bivector, right? Because this is the dual of a bivector, right? This is underneath the red where I've done the cancellation is fi, right? And that is the dual of a bivector, which is a bivector. So this is a bivector part, but it's canceled by this corresponding bivector part here, right? That minus sign is really saving the day. This is a scalar part because I squared is minus 1. So this is another scalar part. And then this alpha beta pseudoscalar part and this pseudoscalar part, they live. So you have a scalar part that lives in alpha squared and beta squared, and you have a pseudoscalar part that lives in alpha beta I. So all we have left to worry about is this guy. Now, a bivector times a bivector, in principle, should produce a grade 0 object, a grade 2 object, and a grade 4 object. Oops. So that's sort of our rule of this is our rule of multiplication. I'm applying the rule of space-time multiplication for two blades, but using blade in sort of the pure sense, right? A pure blade, as our paper describes it. So in this product, potentially, there is this bivector piece. That's a scalar piece. That's a pseudoscalar piece. So a bivector piece could end up there. However, now we can apply this fact that we learned from this paper's organization of notation is that the bivector part of a space-time product of two bivectors, the bivector part is given by this commutator, which this paper defines this way as fg minus gf. And of course, if f and g are the same, this is 0. So that explains that the bivector part of this product is 0, and ergo everything that's left in this reversion square is in fact just scalar and pseudoscalar, where m now is an arbitrary member of, remember, this is completely arbitrary member of the even subalgebra, right? So, which I guess the way the paper would write this is an element of m plus, right? So we have explained that statement. Okay, so continuing on, therefore, the reversion square of an even multivector, remember psi has been defined as a even multivector, right? So the reversion square of an even multivector has only scalar and pseudoscalar parts, only scalar parts and pseudoscalar parts, which means it can be expressed as a complex scalar, right? So we can say psi reversion, right? And we don't need a 0 there because the notation says without a 0, we just assume a 0. That equals some real number alpha plus beta capital I. Now, they use little I here, remember, but we're going to use capital I just for our own continuity's sake. And so once we agree that, hey, this is basically just like a complex number, it has a polar form, right? So they write it as psi reversion is a polar form where the imaginary number I is now rho E, and I'll just write it in there, gamma 0, 1, 2, 3, right? That's the imaginary number I, which they write as little I, right? And some angle beta, where beta and rho are real numbers. And just like exponentiation in Lie algebras, where we frequently write E and we have some matrix up there, right? Literally a matrix. You know, like it could be a 10 by 10 matrix that's in the exponent of E. It's very puzzling to people, but immediately we just understand that this is to be understood as its Taylor expansion, right? It's just its Taylor series. And also, we can apply that Euler formula and just assume that e to the I beta can be broken into cosine beta plus I sine beta. And if you end up with a little minus sign in here, right, if you end up with a minus I beta, then this just becomes a minus sign. So really, all of the rules of complex analysis, where we put things into polar form, apply here just fine. Now, so let's take a quick look to make sure this polar form is consistent, right? Well, rho is a real number, so this is going to equal rho times cosine beta. Well, beta is a real number, so this first part is all a real number. The second part is going to be rho times I sine beta. Well, rho and sine beta, those are real numbers, right? And I is a four-blade, right? So I is gamma 0, 1, 2, 3. It's the basis vector of four blades. So this is clearly going to be, rho sine beta times I, right? So that's a real number times I. So this whole thing is a pseudoscalar. So when you look at this, you see it as a pseudoscalar, right? The reversion square of any even multivector has to be a pseudoscalar. And so now the question is, well, we want to calculate beta and we want to calculate rho, so we can write this reversion square in this form at will. So so let's learn about how to do that. So let's start by saying you took the reversion square of psi and you ultimately wrote it as C plus di, where these are real numbers. I'm running out of Greek letters here that don't have some sort of ambiguity to it, so I'm just going with little c plus little di, where c and d are both real numbers. So c and d are real numbers. And now we just use regular complex analysis to put this in polar form. Rho is the magnitude of this thing, which is c squared plus d squared, the square root of. And you raise this to the power of I times the inverse tangent of d over c. This is sort of elementary complex analysis. D we can write down as the grade 4 part of the reversion square multiplied by I inverse in order to clear the grade 4 basis vector. And C is just the grade 0 part of psi, of the psi of psi reversion square of psi, which we also know by the definition that we had earlier in the paper. We had this definition, right? The magnitude of a multivector M was given by, or the magnitude squared, was given by the reversion squared's grade 0 part, the absolute value of it. So this is what would go inside here. So the absolute value of this is called the magnitude of our reversion square, or is called the magnitude of psi, That's not so important now. It's just sometimes the zero blade part of things shows up in a lot of different contexts. But now that we've got this, we're going to identify rho with this number and beta with this inverse tangent, right? And so now we have sort of formulas for this. Now, if you remember in the paper we're working with, they define beta with a factor of 1/2 in here, right? Inverse tangent d over c. And we might see, I think, why this 1/2 is a way of going. Then this part here will have a factor of 2 in the exponent. But so there is this variation in this process of finding the polar form of a reversion square. There is this variation that has a 1/2 in this definition. We'll try to flesh out exactly why that's there in a moment. So the next thing they notice is that once we've kind of understood this polar form idea, if rho does not equal 0, we can derive from psi an even multivector R defined this way. R is our even multivector multiplied by our reversion square to the minus 1/2. And this property should exist for R. R's reversion squared will be 1, positive 1. So they're saying given any even multivector, we know that we can put its reversion square in this form. And once we've done that, we can define a new even multivector whose reversion square is 1. And this derivation is directly related to the even multivector we were given in the beginning, this arbitrary one. So let's see if we can work through this. Now, at first glance, this kind of looks like sort of weird, right? We're throwing into the denominator the square root of a multivector, right? This is a space-time product of psi with its reversion. Now, we know this has a complex form, and we're taking the complex form to the scalar complex scalar, as I guess what we call it. We know this is a complex scalar, but we're going to take that to the minus 1/2. Well, now that we have polar form, just as with complex numbers, now that we have this form for this reversion, this process is easy to do. We just write down psi times rho e to the I beta to the minus 1/2, which is going to be psi times rho to the 1/2 e to the I, minus 1/2, I minus I beta over 2, right? And now we understand this minus I, as I mentioned before, this minus sign here simply comes in as, once you blow this up into its sort of, its Euler form, this plus sign becomes a minus sign because of this minus sign down here. So this is actually a very easy form to write down. And then the claim is that the reversion square of R equals, does it equal 1, right? Well, we know that it will equal, I just wrote it all out at once. This is R, right? This is how R is literally defined. This is the reversion of R. So notice we take the, I keep wanting to say wave function because it's psi, but what I mean is we take our bivector, we reverse it, and we reverse it with the quadravector. Well, we basically reverse it with the quad vector piece or the complex piece. And it's recursively reversed, right? So you reverse the two, right? You reverse the two multivectors, and then you take the reversion of the two multivectors. But the good news, of course, is that the reversion of I is still I. So this allows us to rewrite this as psi rho inverse, because the two negative square roots or reciprocal square roots of rho come together to form rho to the minus first. And then you get e to the minus I beta over 2. Well, wait a minute. Why isn't that e to the minus I beta? Right? We're combining this e to the minus I beta over 2 with this one, because I reverse is just I. So this over 2, I think, is gone, right? So that should just be a beta, right? That'll be a beta. I'll put my correction in red, which means this is a beta also, right? So let me erase this and write it as a beta, like that. And that action brings the multivector with its reversion like this, right? You've combined those two. But this is by definition, right, or by our calculation actually, right? We've already calculated the reversion of psi with itself. Its reversion squared is given by rho e to the I beta. So this becomes rho e to the I beta. These two things cancel, and you get the scalar 1. So the point of all this is that R is something implied directly from the existence of an even multivector. But what makes R canonical is that we're forcing it to equal this very unique thing, the scalar unit, which we say, okay, that's special enough that we're going to call this canonically related to psi. So that is how R is calculated. And then once we've decided, okay, R is this special sort of multivector that we can generate from any even multivector, we can then sort of reverse the process and say that any even multivector has this canonical R, and a phase, a magnitude and phase, but in particular a phase that connects it to this canonical R, who's defined by R reversion, or its reversion squared, equals 1. Now what's interesting, I guess, is to think about is, okay, so if we think of the electromagnetic field as ultimately going to be an even multivector, the claim is that this form of the electromagnetic field is hard to discover in tensor calculus, but it's very evident in this geometric algebra form. But this now is the canonical form of an even multivector psi. And that's the way this proceeds, right? It says, okay, we've defined R using this technique, and we now have the canonical form of any even multivector psi as being this this square root of rho I b to the theta, just to make sure that that's how we defined it. And that's exactly how we defined it. We just brought in the square root part. Then they say, we shall see that this invariant decomposition has a fundamental significance in Dirac theory. So this decomposition, that's sort of the idea, is any given multivector psi can be decomposed into this form. And then it talks about an important special case of this decomposition is its application to a bivector f. So remember, psi is any even multivector, right? But now, what if we just do it with a bivector f, a straight-up bivector? And in this case, they actually make some symbolic modifications. They say, it is convenient to replace beta over 2 by beta plus pi over 2 and write down this form. A bivector f is rho to the 1/2 canonical r times I. So let's understand how that transition works. And I've written that all down here, where f is our arbitrary bivector, right? The only thing we know about f is it's a bivector, but we know it has this canonical form. There's some beta out there where you can write this bivector as its canonical r and this phase factor. It's not purely a phase factor, right? This is the phase factor because it's got magnitude 1, but it's also got this this overall magnitude factor as well. And he says, okay, in the paper, Hestenes writes, we're going to take beta over 2 and we're going to replace it with some other angle, psi plus pi over 2. They, in the paper, make psi beta. They just redefine the symbols, and I find that a little bit confusing, so I'm going to change it to, everywhere we see beta over 2, we're going to say that equals psi plus pi over 2. So beta would equal 2 psi plus pi, right? And then we just substitute that in for beta over 2. So we substitute this in for beta, right? We take this, substitute in for beta, and we end up with that. Then what are we left with? We're left with the square root of this magnitude, e to the I phi plus pi over 2. Well, well, there's another I there. Whoops, there should be an I here, right? So then e to the I pi over 2, right? This piece, e to the I pi over 2, that becomes I, right? And I commutes with R, so this I pops over to here and lands over there, right? So that's easy enough. And then what's left behind is e to the I phi and the square root of this magnitude. Then, since bivectors commute with the quadrivector basis vector, I can move R all the way over, I can move Ri all the way over, and I can write it in this form, where I have Ri is where I have the dual of this canonical vector sort of sandwiched in the middle. And then I just define this canonical form F to be rho 1/2 times the dual of R, and I put that out in front, and I'm left with this e to the I phi factor. And now I really do have a canonical bivector and a pure phase, So that's the process here. It's not that confusing, but if you do check, I mean, it's pretty straightforward. It's not something I would have thought of, but that's why you have researchers who study mathematician for a living. They come up with these things. But then you take a look at, okay, taking this canonical version, what is the reversion squared of little f? And we can write down, well, little f is rho times the dual of the canonical form r. Well, the reversion, it's rho to 1/2, and the reversion is another factor of rho to the 1/2, so you end up with rho, and then you have this recursive reversion of I and r, but I reversion is just I, so you end up with a -1 there, so that's easy. And then you end up with minus rho RR reversion, but RR reversion is 1 because we've defined it that way. We built R so that its reversion square is 1, so you end up with minus rho. Now rho is greater than 0, it's always greater than 0, so minus rho is less than 0. So if we calculated the signature of f, we take its reversion square over its magnitude. And remember, we defined its magnitude very cleanly in the beginning as the absolute value of the 0 grade portion of FF reversion. So that ends up being minus rho over rho, and so the signature of f is -1. And that's about as far as we need to go with the Hestenes paper, right? We have achieved this story right here. We've achieved an understanding of this expression. And if we go back to the paper that we are studying ourselves, what we see is basically the same process, right? They end up in exactly the same place. Now, you'll notice that they define phi with that factor of 1/2, but we saw plenty of places where we saw that final substitution that Hestenes made to basically get rid of a 1/2 that floated into the problem. And this paper just gets rid of it at the front end, basically. So, and then, of course, there's this expression here, which is literally just the inverse of calculating f, right? These two are inversely related. So the point is that the idea is that we can always take any bivector f, create a canonical form of f that has a definite negative signature, and they choose a negative signature as for some reason. Now, canonical is kind of interesting, right? When I use the word canonical in previous work, what I usually mean is it's sort of forced upon us. In this case, there are some decisions that are being made, like, for example, this whole idea of like, oh, we really dig this r because r inverse equals 1. We like this 1. So, it's certainly possible to do 100% of the time, but being canonical is it's more of being a convenience in this case. But I don't think there's any super official meaning for the word canonical in math and physics necessarily. It just means something that you can do all the time. And sometimes there's only one thing that you can do, and other times there are many things you can do, but one of them is the best, or the most convenient. And I think that's what's going on here. Okay, so now we understand that any bivector, we have this canonical form that has a phase factor, and we know how to calculate those phase factors. And this factor of 2 is not so hard to understand anymore. And now we can move on to section 3.5.2. And I think we'll do that in our next lesson. This is a good place to stop. And the next lesson we will take up the subject of bivectors, products with bivectors, which you've actually already studied, right? We know this. We know this statement, for example. But we don't know it in this context with the canonical form. So we've learned something important, and I'll see you next time.